Thanks. So today is a great day for astrophysics, in part because of the recent announcement of the Nobel Prize in Physics that went to the work on black holes by Andrea Ghez, Reinhard Genzel, and Roger Penrose. But for our local community, it's also a great day because we are welcoming Rashid Sunyaev, who is going to tell us about some really exciting science. Rashid in this audience does not need much of an introduction, but just for the benefit of younger people in the audience, I will say a few words about him. Rashid did his studies in astrophysics in Moscow Institute of Physics and Technology, as many people, some of the people who are listening to this presentation right now. He got his PhD in 1968 and has worked in different topics in astrophysics since then. He has been the head of the theory department in the Moscow Institute for Space Research, as well as he has been a scientist associated for a long time with Max Planck Institute in Garching, in which he has been a director for quite a while. His scientific interests are extremely broad and reflect a very good taste in cosmology and high-energy astrophysics. He has done seminal contributions in a theory of cosmic microwave background, Sunyaev-Zeldovich effect that bears his name, as well as in physics of accretion disks. Not only has he worked on theory in astrophysics, he has also done tremendous contributions in the development of missions that are delivering a lot of beautiful science. So he has been a PI on a quant module on a Soviet space station Mir. Then he led the project Granat that discovered a lot of interesting, made a lot of interesting X-ray discoveries, been a huge part of the Integral project, joined the German-Russian project. And today he will tell us beautiful things about another Russian-German project, SRG, eRosita. So over the years, Rashid has accumulated so many different prizes that it would probably take me 5 minutes to just list all of them. I'll mention only things such as Brun-Rossi Prize, Hahnemann Prize, Russell Prize, Gruber Prize, Kyoto Prize, Ben Franklin Medal, and memberships in all sorts of different academies. With that, and I'll mention also that he has produced a great cohort of disciples and colleagues who have worked with him over the years, and some of them will be featured through this talk. So without further ado, Rashid, please take the steering wheel.
Thank you very much, and it is great pleasure for me to be again in Princeton. After this, I was unable to come to Princeton practically 1 year, just due to the well-known problem with this great, not great, but very bad virus. But I have my usual story that I have much more slides than I can really show for during this talk. I will speak today about observatory. You see here, this is a spectrum, a Spectre RG observatory, and let us start just with the image of the spacecraft. It is spacecraft produced by the Lavochkin Association near Moscow. It's working, I don't know what to do. It's working absolutely perfectly. We are enormously happy with spacecraft till now. And there are two instruments, Arctic C, you see it, Russian, which is produced, I will tell about this later. And there is also eRosita, giant instrument. I remember how I started negotiations about this device to observe the whole sky, to make and to discover 100,000 clusters of galaxies. And Günther Heisinger, now the scientific director of European Space Agency, at that time, director of Max Planck Institute for Extraterrestrial Physics in Garching, he told me, yes, we have tiny device which left after Abrixas. I forgot it was 30 or 50 kilograms, and we can give it to you. But it was obvious that this device can observe from the whole sky only maybe 1,000 or few thousand clusters. I told no, or 100 or not. We had very long negotiations, and finally this device grew up, you see here, for 808 kilograms, 3.5 meter length, and 1.9 meter diameter. And these are real people from Lavachkin industry. We were waiting a lot. If I will have enough time, in the end, I will show you 2 slides. The story started of this spacecraft in reality in 1987. It's practically half of my life went to launch this spacecraft. But launch was as usual. This was 4th Proton Launch, which was where our group was participating in the science, in the missions which Roman already mentioned. And launch went beautifully. This was first launch to the L2 point of the Sun-Earth system. Sun is somewhere there in 150 million kilometers, as you know. This is Earth, written in Russian, excuse me, and this is Moon orbit. And we have very strange orbit, I can tell you, because this is orbit trajectory of the projection of our trajectory to the ecliptic plane. And you see it's very elongated. And what is important to say is that we were flying a little more than 100 days until we went to this orbit finally. And this 100 days, this flight, we were performing adjustments, calibration, and very long observation of interesting areas. And this was performance verification, and we found that both devices are working very well. There were a lot of complications, especially with eRosita, but finally everything is working. My German colleagues do not understand why sometimes detectors behave not in the best way, but it seems that you just switching off and switching on, and everything is fortunately working again. And this is the trajectory. In half a year, we are making 1 revolution, and this revolution, at the same time, we are getting full sky map, and this comes every half a year. This is very good for us, and we made first revolution, and now half of the second revolution. Therefore, we have 1 1/2 of the, I will show you map of the first sky survey. I have with me pictures, but I will not show you, but we now have also half of the sky in addition, second time. And this is very interesting and important. Then you see now Sun, Earth again, Moon, everything is from one side of the spacecraft. Everybody knows that this is enormously good for CMB spacecraft, for microwave spacecraft, but in our case, it is also very good because we are able to work 24 hours per day, and efficiency is, as I understood from our technical people and from German colleagues, that efficiency is, we are observing 96% of all time during half a year, which is a lot. But now spacecraft, in addition, rotates around its axis, which is directed to the Earth and Sun. And it makes revolution every 4 hours. Every source on the sky is observed 6 times per day, once in a half a year. And it is important, we can see, we can observe or look for short time variability of the sources. But we return to the same position, to the same source only in a half of year. Yes, I wish to show you these our scans. You see here, these were initial scans where we tested. It's 1 degree white and 360 degrees big circle. Therefore, we are getting this another scan, and this was a disaster. You see here, we lost 1 day, and there is a gap. There are beautiful verses of Russian poet Nekrasov, but I will not translate now, but it shows that how the peasants have the fields, and in the field there is one empty field. And what is a tragedy for the family? I showed this picture many times to our industry and told, if you will not work one day, I will read you and to press that great verses. Okay, let's go further. Spacecraft is, mechanics of the spacecraft and electronics are very well working. And we introduced, this was Igor Lapshov in our group, who introduced the new, he demonstrated that the best for observation is the scanning mode. When we are scanning the sky in the selected regions of the sky with dimensions less than 12.5 to 12.5 degrees. And you see here. And this gave us possibility during performance verification to observe, I think we observed 12 deep fields. And this is one of the deep fields, Lockman Hole. I think that majority of you know very well that Lockman Hole is the region with which Lockman, who was very young at that time, he discovered that this is the region of the minimal 21 centimeter column density on the sky. This was the reason why Chandra spent a lot of time observing tiny regions here, but we observed it, you see here, 20 square degrees. And this 20 square degrees, we scanned in this way, and we discovered here, during maybe 30,000 seconds, 6,000 X-ray sources on 20 square degrees. You see here immediately that we have 300 sources. All these are X-ray sources. It's not optical picture. It's X-rays from eRosita. And you see also that we have 270 extended sources. Till now, we confirmed 185 clusters of galaxies on this territory. This really very deep field because we have more than, we have practically 10 objects per 10 clusters of galaxies per square degree. This immediately shows that we can, on the whole sky, we will give similar exposure, which is impossible for us. We will get several 100,000 of clusters. Let's go further. Now, in 2008, there were very long negotiations. We started this project, I told you, in '87. Then there was interruption in 1987. Then there was interruption in 2003. We were closed. In 2005, we were alive again. And in 2008, Roscosmos, Russian Space Agency, and DLR, German Air and Space Agency, made the statement and included it into the Memorandum of Understanding. That Germany supplies us with Crazy Coincidence telescope according to specification which we agreed, and for the data processing and publication of results of this mission, on one half of the sky will be responsible Russian scientists, and German scientists will be responsible for all results from another hemisphere. This is separation, center of our galaxy, North galactic pole, South galactic pole, and you see we are working with data from this side in the Russian Space Research Institute and in Max Planck Institute of Extraterrestrial Physics. People are working and in whole Germany with data from this side. Yes, Russian device, Arctic Sea, it has 7 Crazy Coincidence mirrors, and it has, in addition, 7 detectors, cadmium telluride, and there are, it was built detectors fully, and other parts, part in ET, part in the Russian Federal Nuclear Center, where Zeldovich and Sakharov, if I will have time, I will show the photo. They helped a lot to this mission. This center produced this telescope. And this was first telescope, X-ray grazing telescope in Russia. And Then we compared these mirrors because one friend of Mikhail Pavlinsky, PI of this instrument, they were together learning in this city, in the school, and he was working in Marshall Space Flight Center and was leading production of crazy coincidence mirrors. They agreed that they will compare mirrors, and I can tell you that Marshall Space Flight Center were better, and then we decided to fly these mirrors. This was a decision, therefore there is also American X-ray mirrors on this system. 7 detectors, 7 mirrors, energy range from 5 to 30 TeV, field of view, eRosita has 1 degree and he is 34, but eRosita has very modest time resolution of the order of 50 or 100, even hundreds milliseconds. It's question how the CCD is, data of CCD are taken out from the matrix. And here in the cadmium telluride detector, characteristic time resolution and is 27 microseconds. Okay, this is the effective area of the detectors and mirrors, and you see eRosita. Oh, sorry. One second, I will return. Yes, it is eRosita. You see, it's very soft. It's connected with the, how to say, the mirrors made from gold, and there is the, how to say, the atomic envelope, and this is the reason why there is so strong cut for the absorption. You see here the effective area of eRosita, and then it drops very rapidly to 10 TeV. We do not observe at 10 TeV at all. And Arctic Sea, it is here. It's very good starting of 4-5 TeV, and then it goes here up to 30 TeV, where we are working okay. And this is best American spacecraft in this region. It is no star. It is practically twice, has twice higher effective surface area, but much smaller field of view. And I will show you, this is the galactic center region. You see Sagittarius A star and many well-known sources. These mosaics, NuSTAR has very small field of view, not very, but small field of view, and they're pointing to many places. It's 144 kilosecond observation of galactic center region. This is Arctic Sea scanning galactic center, and this is 4.8 kiloseconds. This is the power of the instrument, that we can do many things very rapidly. Timing, this is a well-known pulsar. It's here written, PSR BP1509 minus 58, and you see it is pulsing. You see it here, and these are Chandra data. We have the eRosita data image also. Chandra image, how the particles flow from the pulsar is producing shock here, and this is pulsar nebula, which is also very bright in X-rays. But these are data of Arctic Sea. This is radiation from 4 to 12 keV, where it was detected. Yes, this is the focal plane of eRosita. I also should show eRosita has 7 mirror system and 7 CCD detectors. I'm showing this only to you that 7 CCD detectors are working in space, and temperature practically during a year is very close to 84, minus 84 Celsius. It's passive cooling, and on this orbit, passive cooling is working very well. Now I will show you, this is a picture of Marat Gilfanov. We discussed a lot, but then many people in Institute in Moscow, Space Research Institute, and in Sternberg Astronomical Institute are interested in the sources in the galactic reach. And this is a region of galactic reach, 25 square degrees, in 20 degrees from the galactic center. Galactic center is in that direction. And you see here beautiful, a lot of different sources. I myself was impressed when I saw this. I knew that there will be a lot of X-ray objects on the sky. But when we discovered, you see here, star-forming region, and all these points are young, just just very young stars. And you see how many they are here, and this is one pointing. This is the Tauri star, well known also, but you see how bright it is in X-rays. This is very hot supernova, very interesting. You see it. This is older supernova. I will tell you about the colors here because they are very important. It's normal star, stellar corona, and this is pulsar. You see, it's normal pulsar, not X-ray pulsar, but not X-ray pulsar, but it radiates in X-rays. All together here of the order of, okay, there are 6,000 sources here, a lot. There are many flaring stars, white dwarfs, pulsars. There are many much less bright supernovae remnants, but extremely interesting for all of us is the emission of the diffuse gas. You see here this red picture, you see here green, and this again red region. This is all hot gas in our galaxy. It's necessary to investigate at what distance is it, this gas, but there is a lot of hot diffuse gas. And here on this picture, this RGB picture, you see blue and green colors correspond to high energies of photons. They are radiated with the gas with temperature millions and 10 of millions Kelvin. The red color, this much colder gas with temperatures of 100,000 and 1 million degrees. Therefore, this is colder gas, and for example, this is very hot gas. And we see it also, we know all these things. This demonstrates you how important are these scanning observations of selected regions on the sky. We are extremely sensitive, and this is few tenths of kiloseconds. You're getting a lot of science, completely absolutely different scientific, for people with absolutely different scientific interests. Now I will show you, I will show it also on the map. There is I told you that we made the scan of the whole sky. During whole scan, we are observing every object during day, during 6 passes through object, less than 40 seconds each. This is Cygnus loop. And you see how bright is it in 200 seconds for eRosita. Very, very bright. A lot of photons. With these photons, we can also, this hot gas, supernova remnant, and you see the spectrum of this region, only this internal circle. And you see here a lot of lines. I hope that you see, Roman, do you see this? Can you read oxygen, iron, neon, magnesium, yes, silicon? You see it, yes? Okay, thank you. You see it, and this is photons which were captured in 200 seconds. I knew that it should be, but when you see this, you really are impressed. And this is now here tenths of kiloseconds observation of supernova 87A in LMC, in Large Magellanic Cloud. For me, this supernova is great because we discovered there how gamma photons, after many scatterings due to recoil, are producing hard X-ray radiation just due to the quantization. But this is a spectrum now from the shock wave, and black curve you see here, nitrogen, oxygen, neon, both lines, hydrogen-like neon, and helium-like neon, magnesium, silicon, sulfur, you see it here, and this is in comparison data from XMM Newton with comparable duration of exposition. And you see spectroscopy is not worse for eRosita. We are very happy with this. Now I told you that we finished first sky survey. And all of you heard a lot about sky survey of Joachim Trümper using Rosat, which was the best in the world during 30 years. This is our map. And I like this was idea of Andrea Merlot to write. I was against, to be honest, to write the brightest sources because we are interested in the most. You see here, there is 1 million of point sources. Do you see these points, white points? These all are extragalactic objects and stars of our galaxy. There is an enormous amount of these objects. But there are sources which everybody knows. The brightest source is Scorpio X1. It's enormously big. It's big. I have no time to show you the dust scattering halo. It's so big because we see from it the dust scattering halo, and this dust scattering halo has huge dimension. You see these points, every point, these are our point sources. And this is Scorpio X1. It's so bright that we see instead 2 scatterings, often only 1 scattering, which is improbable, but they are coming. And second, there is a dust halo. We see now dust halo from many tens of brightest sources, especially when they are variable. But we are very interested in clusters of galaxies, and Princeton is today great center for clusters of galaxies. And look, this Coma cluster, Virgo cluster, Shapley supercluster, we see it. Centaurus cluster of galaxy, what else? Perseus cluster, extremely bright. There are many supernova remnants, you can read much faster than I, and this is large Magellanic cloud. We see Orion Nebula with a lot of with hot gas and also with star-forming region. A lot of different things, and I showed you already, this is Cygnus loop, and I showed you the spectrum of Cygnus loop, but it's really very, very bright. You see beautiful picture. This is a result of 1 year, and here there are 400 millions of photons, just here. They are also in 3 spectral band. I will show you again now without, how to say, without showing the brightest sources. We have billion of X-ray sources. Milky Way, you see this is the Milky Way. Yes. And Milky Way, I am very impressed. Look that this Milky Way is very dark here. I will tell a few words later. Everybody knows this. But in X-rays, when I'm giving in Russia talks, I usually show Milky Way. But I think that everybody in Princeton have seen Milky Way and how bright is it. In X-rays, it's extremely dark, plus a lot of bright sources. Now there are 3 colors with energies 400 million photons from 300 eV to 2.3 keV. And this is all detected during half a year. Red color corresponds to photons with soft photons from 0.3 to 0.6 keV, green 0.6 to 1 keV, and blue 1 to 2.3 keV. And it is great. You see here region cold regions. You see where halo is radiating in the, or something around in the galaxies radiating in the soft X-rays. But there are also regions, for example, majority we see in the plane of the galaxy and in bulge of the galaxy, a lot of blue objects. These are binary X-ray sources, very, very bright. We see a lot of things. But I was amused from the beginning with this enormous picture, which is much more, it's present on Rosat map, but it's not so illuminating because our sensitivity is significantly higher than Rosat. And you see here, this is North Polar Spur. and we see it very, very bright. What is great discovery of eRosita? You see here, and we now with a second, we have see it much better. We see also similar thing on the south, which is maybe a few times less bright than what is in the north. You see these things, it is great, and this Cygnus loop, as you see, there are many other things. Yes, and first SRG all-sky survey allowed us to construct a map containing almost 8 times more X-ray sources than the former world best map of the Rosat spacecraft obtained in 1980. Joachim Trumper is very good elder friend of mine, and he especially came and told Rashid, my congratulations. It's really a dream. Now your map, after half a year, is much better. We dream to have 8 scans of the sky so that the sensitivity will be maybe 8 or 5 or 10 times higher than of this map. We will discover a lot more, much more sources, and this will be very interesting. But I can tell you that now we cross-correlated the map and millions of sources here with optical data and radio data and so on. And we can tell you that 3/4 of a million objects on this map are distant quasars and empty galactic nuclei, 3/4, which are powered by accretion of matter onto supermassive black holes in the centers of the galaxy. These objects are very far beyond Milky Way at distances of hundreds of millions and billions of light years. But we see also 20,000 extended objects, mainly clusters and rich groups of galaxies with hot gas, and more than 200,000 galactic stars with active coronae. A lot of them, of these stars, and it's very easy now to remove them. For example, you are taking Gaia data with peculiar velocity and so on, and just you separate this map, a million of sources, to 2 families immediately. This is also very exciting, and very exciting to see how very young students are doing this easily. This is also very impressive. Yes, I will show you, yes, this map, yes, before I will tell you very interesting thing. I told you that the half of data, for example, this site is German, and no one I'm responsible for this, that no, even we have all complete, all data in our institute, in our archive, but no one person from Russia is entering this site. It's completely forbidden, except if there is agreement that calibration group should look to that or another source. And I can tell you that when we agreed to make this joint map, there were one group, Brunner and Sanders, they did this right side of the book, and Churazov and Gilfanov, Eugene Churazov and Marat Gilfanov, you certainly know them, they made themselves the left side. And then I was during the time when people decided to, how to say, to merge 2 maps. And it was enormous. Immediately there was no difference, even significant part of software is different. But everything was absolutely smooth, no, sharp boundaries connected with this separation of the sky. We can work, and different groups can produce maps and join them together, and this was very good check of that everything works well. Okay, now I will show you only 2 colors. One color is, yes, the color from 0.7 to 2.3 keV, you see it. Now I'm showing you only the part for which hemisphere, which analyzed by Russian eRosita consortium. And you see here, this is the North Polar Spur. You see it. This is Southern Spur, which we discovered. How bright is it? You see, just on opposite side. This Cygnus loop. But then you see millions of sources, and rather weak absorption in the galactic plane. You see it, and we are checking really gas here is a little above plane of the galaxy. It's a lot of well-known things. But let us go further. And this is map also made by Marat Gilfanov. You see here the band from 0.3 to 0.7 keV. You practically do not see here a lot of sources. They are there, but diffuse radiation is so bright that, you know, they contribute a lot to the background, that it's difficult to see, to recognize immediately these point sources. And this is the absorption in the plane of the galaxy. It also is enormously strong. And obviously we dream to use all these maps and maps from the future scans. I told you that we will have 8 scans and then bring them together to create much more sensitive map. We are looking for is there really local bubble? Does it exist? We will see for heliosphere where the solar wind starts to interact with local interstellar matter and, oh, excuse me, this is my Russian, and with the gas of the halo in our galaxy. We will see also this and we will study. A lot of people in Princeton and everywhere in the world are interested in exoplanets. And I came to Marat Gilfanov and told him, Marat, we should correlate to map or catalog of the stars with exoplanets with our points, with our X-ray detected stars. But we have, as I told you, we have 200,000, and there are only on our side of the sky, there is only 600 nearby stars with exoplanets. I'm not counting the Kepler field, which is much deeper, as you know. And we detected X-rays from 60 stars with known exoplanets. And this demonstrates that these 60 stars in X-rays, the luminosity of the stellar corona is 1,000 or many hundreds times higher than our solar corona, just to permit us to detect these objects. Then you see, obviously very interesting, what occurs with exoplanets in habitable zone. And result is the following. Till now, we do not see in X-rays no one star with exoplanets in habitable zone. Therefore, till now, it seems that they are more safe than majority of these objects. Yes, I will go now to clusters of galaxies. Everybody knows, I think, that what is a clusters, how you see here thousands of galaxies which are moving with huge velocities of the order of 1,000 kilometers per second, that there is hot intergalactic intercluster gas, which we can investigate with very small density, only one particle, one electron per thousandth, per 1,000 cubic centimeters. I think it is 1 liter. Yes, we can observe this. And this gas contributes 15% of the mass, and we are investigating now it. But I wish to show you that there are several gravitational lenses in this Able 2218 cluster, and this is also the result of huge gravitational potential. Now we are discovering clusters of galaxies, and in many of these clusters, optical astronomers are finding gravitational lenses which permit to observe very distant galaxies, once amplified by the gravity lens and then by optical telescope. Yes, this is a picture of coma cluster in hard X-rays by Arctic Sea instruments from 4 to 15 keV. This work of Pavlinsky, Burenin, and Sazonov. And this is Planck image. But I will show you now the eRosita image. And this is 3 to 3 degrees, you see field. And This is more than 1.6 or 1.7 degree. This is a coma cluster of galaxies. You see it. This is maybe 60 or 70 kiloseconds of observations. And this is a subcluster which went through coma and now returns back. And you see there is a tail, there is a breach with a lot of hot gas here and a lot of strong shocks. We see the cooling fronts here. I can tell you this is a decrease of temperature to distant periphery. And this is beautiful results. We are very happy, but also very impressive is that there are tens of distant clusters, many distant clusters in this 3 to 3 degrees square degrees field. It's a lot of them because it's very deep. We see clusters of galaxies and they're very different. It's important that as that picture by Planck shows you the same elongation and some, some details you see here like straight things on the image too. There is a lot of synergy between these objects. Now I will tell you a little about the Atacama Cosmology telescope results. As you know, a week maybe ago, Atacama Cosmology telescope provided us great results of their shallow sky survey, 13,000 square degrees and on the sky. And this is today biggest collection of the clusters of galaxies obtained using that effect. And you see the images on the sky, this Russian part of the sky, this is DE. I don't like to speak, let us not speak Russian, the German part. It is where Russians are responsible for data processing and Germans are responsible for data processing. And you see here, we analyze this part of the, this footprint of the act. Altogether there was 4,200. On our side, it was much less. It's only 1,600. And I can tell you that we see on the whole extragalactic part of our part of the sky on 20,000 degrees, square degrees, we see 8,300 clusters in X-rays. It's a lot. And SRG, yes. And on the footprint of ACT in this region where ACT observed on our side, we see today 4,200 clusters of galaxies. ACT sees 1,600. And I can tell you we have the flux X-rays detected, but common footprint is 600, 700 clusters independently detected in the X-rays and in microwave. And it's very interesting. There is deep field ACT D56. We see here, they see in the deep field 180 clusters, we see 260. And this picture is prepared by Ildar Habibulin. He is our young postdoc, and Eugene Churazov, whom many of you know. But I will show now the picture which was prepared by Marat Gilfanov. And here you see not only the same amount, because they are working independently and then we are comparing data. You see here total number of ACT sources in this field, 1591, and they are much, this red part, much with eRosita extended sources, 722. Matches with eRosita point sources, no clusters, 438. These are blue, you see these blue objects. And no match with any eRosita sources yet. It is just green crosses here. It is 431 objects. And there are 3 1,300 eRosita good cluster candidates not included into ACT catalog, just in the same Atacama Cosmology telescope field. It's rather interesting, and you see the distribution over the sky. Up to redshift 0.6, practically all clusters of galaxies coincide, then no. And it was predicted, SPT-3G, when they decided to install 15,000 bolometers in the South Pole Telescope focal plane. Then there is paper of Benson et al. 2014. They planned for 1 year that they will achieve this sensitivity and will discover these clusters of galaxies only on 2,500 square degrees, because they're making deep sky survey in this region. But these are Planck, red are Planck clusters, and black are objects already detected by South Pole Telescope. And this is sensitivity which was predicted by eRosita. We have a little better sensitivity today, but I can tell you only one thing. You see that at small redshifts here, eRosita is much up to redshift maybe 0.5. eRosita is much better than ground-based telescope, even in the deep fields. And at higher redshift, just due to properties of the SZ effect, because brightness doesn't depend on redshift, you see that eRosita loses, and in principle, ground-based instrument might be much more successful this time. This is just as that effect, and you see this picture. Now, I can very rapidly tell you a few words about the second sky survey, and what we have here. We already have 50% of the sky is covered, and we are very happy. You see also, I should mention this, that these scans, the big circles, are intersecting in the north and south galactic ecliptic poles. And here we have region of sky survey, and therefore much higher sensitivity of deep sky survey, and therefore our picture is much deeper. This first observation, you see immediately on 2 multiplied to 2 degrees, square degrees, we see immediately, just it's possible to see with the eye immediately, galaxy cluster at redshift 0.28, its quasar at redshift 2.7, and there are many other objects which were observed before by Planck or optical instruments. But it's interesting, and what we are doing first, we obviously will summarize these 2 scans and we'll discover a lot, no, at least twice more objects. But we can also compare results of 2 sky surveys and look for variability of hundreds of thousands of X-ray sources during a half of the year. And I can tell you that this is a lot of such objects. There are many tens of the sources which already we found, which changed their brightness more than 10 times. What is the reason? There are several. We are looking for gamma ray burst afterglows, and we are especially interested in the tidal disruption events. I can tell you that during last week, we are discovering from 1 to 2 objects which became 10 times brighter than they were half a year. And this is, every day it is 360 degrees on the sky. We are observing, and there is huge variability of our sky, and we are very glad. But everybody knows this, how tidal disruption event, it's going then, how to say, star is going near supermassive black hole, and when tidal forces become very strong, part of the gas is disrupted, part of the gas goes to infinity, part of it is captured. You see here, and this light curve, and we can observe in half a year this maxima easily, because these objects become very bright.
Rashid,
now I can tell you in each. Excuse me?
About
okay.
okay.
Yes, thank you very much. Yes. I can show you here that what we are doing, this especially Alex Mishrikov and his group of people around him, they developed the SRG-Z program, which based on machine learning and neural network programs. And what they are doing, they are analyzing 500,000 of X-ray sources, and just they are looking for the most distant objects on our maps. For example, they discovered during first sky survey 100 objects at Z higher than 3. We can continue to search for the most distant quasars using existing photometric data in very narrow bands, spectral bands, and 90% of success. With precision, few percent, this selection and spectroscopic redshifts are the same. But I should mention that Russia hasn't big telescopes. These two quasars with redshift 4.1 and 4.2, they are discovered by telescope 1.5 meter class. And these telescopes are making, they're very, very bright, unusually bright. This is on 6 meter telescope. You see redshift 4.6. There is, by this telescope also, we discovered 5.4 redshift quasar, but we are much more impressed by these objects with redshift 6.18. You see X-rays, it was known before us, but we discovered it in our X-ray, on our X-ray map, and then estimated it redshift, and then discovered that other people observed it earlier. This Pavel Medvedev, he is first author, he discovered this object. This is the brightest X-ray quasar on the whole among all objects which people know till now. You see, its luminosity is of the order of 3 times 10 power 44 ergs per second, only in X-rays. It's very impressive, and we are very happy with this result. Yes, and just before I show you 2 historic pictures in the last minutes, I can tell you that we are enormously grateful to many people in the Lavachkin industry, because they are working with the spacecraft every day. These 2 giant antennae in Bear Lakes near Moscow, this antenna, and Ussurisk 70 meter, it's near Russian boundary with North Korea and China. And people who are working on these technical people in MP and TK, who are every day sending comments and receiving scientific data and send them to scientists. It's very, very interesting and important for us. But I will show you only 2 pictures in addition, sorry. Oh, this 1987 Moscow, 30th anniversary of the launch of first Sputnik. International meeting in Moscow. This is Zeldovich, Sakharov, this is me, and this Ralph Sagdeev, key director of that time. And this is first design of Spectrum X, old concept, and there was huge collaboration brought with UK, Denmark, Italy, USA, Germany, Switzerland, Israel, with many countries. Proton launch was expected. Then it's our drama, great changes in the Soviet Union, mission was delayed and canceled, then many devices were ready to fly. This device is flying jet, the name for our mission was Joint European X-ray Telescope, together with UK, Italy, Germany. You see it here. It is now on the Swift spacecraft, American spacecraft. There are 2 small devices which are also flying on other instruments, but other things. I'm coming to Lavachkin, see the huge mock-ups of this spacecraft, and it's obviously great unhappiness because practically 20 years came without of life, came without any result. I think that it's time for me to finish. Thank you very much. Roman, for your patience as chairman. Yes.
Well, Rashid, thank you very much for such an enthusiastic and interesting report on this, beautiful discoveries made with this spacecraft. So we'll now have a number of questions. I'm sure there will be a lot of questions. We have only limited amount of time. There is a schedule for online meetings with Rashid. As you know, Rashid is a distinguished visiting professor at the IS, so it's kind of one of his duties to talk to local people. And right now the schedule is full, but please do feel free to add yourself up to other people's slots to have more conversations regarding these signs. So the first question would go to Elliot Quarter.
Hi, Rashid. You mentioned, I think, that each field is viewed with eRosita 6 times a day. I wonder if you could tell us, is there any attempt to analyze whether there are X-ray sources that are variable on that?
Oh, yes, certainly. People are working on this, and we are checking, we are trying to understand physics. But there is a group of people who are working on this, both in Germany and in Russia. There are people who are working with this data and trying to find this short time variability. I can tell you obvious thing. For example, there is a lot of stars which are variable on this time scale, and we know this watching our sun.
Are there plans for public alerts associated?
Yes, there are. Till now, we have enough forces only to make public alerts about the transients, which are really, how to say, very impressive, and there are great changes in the for the quasars or galaxies. We are looking for TDE mainly, or gamma burst afterglows. For example, when nobody detected gamma burst itself, but there is afterglow. We are looking for this, for such events also. But obviously, we are planning and we are doing alerts about this. We are using mainly the astronomer telegrams, and there are maybe dozens of telegrams in 12 years.
Okay, next short question and short answer, Joe Dunkley.
Oh yeah, just it's amazing to see all the clusters and amazing to compare to ACT. So thank you. But what's your time scale for sharing data with either the world or with smaller?
I think we can do this. In reality, I proposed this many times before the launch. Maybe you know, but we can do this and we can discuss this obviously. You know, it is. Thank you for speaking about this. But these are beautiful data, and it's possible to get a lot of synergy. But you know, we wanted to publish our own catalog, but then we forget about it and just investigated what is in ACT footprint. And I told today first results. They are not published, not mentioned anywhere. But I am glad that people from Princeton ACT team hear this. Thank you.
Okay, Netta.
Well, congratulations, Rashid, on a very successful mission. Wonderful. I have a quick question, whether you can say something about the implications for the physics of the comparison between the clusters X-ray and the SZ from the data that you have so far.
I can tell you that we have a lot of implications on COMA, because COMA is very well covered by Planck. It is resolved by Planck in microwave, and we have also data with Planck has 5 to 10 arc-minute angular resolution, but we have angular resolution better from in the center of the field 10 arcseconds, in the boundaries of the order of 25 or 30 arcsecond. It's a lot of work, you know, but people are doing. And I hope that we will get a lot from these comparisons there. And obviously everything will be, yes, and this data with some time will be open for community. There is also a decision in the Russian community. Question is only when we will have good calibration and can go. You understand me that we will be absolutely safe that all science which we are producing is well done. But it is a very good question.
We have a time for a couple more questions. I will ask one of them actually. So Rashid, in this picture of the galactic reach in the beginning, you were showing this neutron star, which you showed is not an X-ray pulsar. Was it, I mean, it sort of also looked a bit extended. So was it just a pulsar wind nebula of this pulsar, or is it a young?
There is a pulsar. It's not X-ray pulsar, it's radio pulsar.
Right.
But this radio pulsar, and there is a nebula around. This like Crab Nebula, you know, it's just, but it is much more active thing, and there is flow. I don't like to speak a lot about that source because there are also beautiful chapter data, but we were very happy because much faster we got all key things. We are just learning how to study other things with this performance verification, long exposures. After 4 years of scanning of the whole sky, we observatory will work at least what industry guarantees us 2.5 years just as observatory observing different objects on the sky, but we cannot compete for point objects with Chandra. However, just observing regions on the sky, we are really the best. I showed you that 20 degrees, 100 square degrees on the sky. We are doing this fast and with very high efficiency.
Also, in terms of galactic science, do you have plans or a team to work on sort of more mundane objects such as white dwarfs, you know, in cataclysmic variables?
Yes, there are people already who are getting this data, and I can tell you that there is a group of people. It's very interesting because, for example, Turkey is providing us to Arctic Sea team the time on the telescope, Russian telescope on the territory, and in return they got also together. They are working together on cataclysmic variables now. It's possible to make collaboration.
Okay, great. I don't see any more raised hands, and we are over time. So, you know, we are basically thanking Rashid again for his great talk, for this intellectual contribution of this morning. And we'll see him back again in half an hour at the Bacal lunch. So see you all at that event.